Okay, so let's go ahead and get started. The classwork that I had you guys do and the homework was all really to try to get at this equation. 1 over CQ is equal to 1 over C1 plus 1 over C2 for the various symmetries that we applied Gauss's law for. So in class we did the planar symmetry, the spherical symmetry, and the homework was based on the cylindrical symmetry. And so what I had wanted you to do here was to go about this two ways. One is to find what the capacitance is just by calculating what the difference in electric potential is from the outside of the inner shell to the inside of the outermost shell. And then to apply this equation to show that you end up getting the same thing. And that's really, like I said, to get at proving that this equation is true. So for the homework, what we had was these cylindrical shells. Where this is some inner radius of A, some inner radius of B, and some inner radius of C. And each one of these shells has some thickness of T. And then this was cylindrical, so it kind of came out like this. So the first thing that we want to do here to find what the difference in electric potential is between this inner surface and this, this outer surface of the inner shell and the inner surface of the outermost shell is to find what the change in electric potential is, or the difference in electric potential between these 2 points. And in order to do that, what we need to do is we need to apply Gauss's law to find what the electric field is in the 3 regions that we're looking at over this interval. And so we can start by writing down Gauss's law. Gauss's law says the integral of E dot ds is equal to Q in divided by epsilon naught. And because this is a cylindrically symmetric case, what that means is if I'm going to draw my Gaussian surface between A plus T and B, then I have these Gaussian cylinders like this. Okay. So if this has some total length of L, then the left-hand side of Gauss's law is going to reduce so that this is going to be E times S, which is going to be E times 2 pi times R times L. Okay? Now, for this particular example, I didn't tell you that there was any particular charge on here. But whenever you calculate capacitance, you can define some charge that you want to put on the shell. And then ultimately, when you use the definition of capacitance, that is that C is equal to the magnitude of Q divided by delta V, when you use this, the charge, whatever charge you decide to put in here, ends up canceling. Okay, so if I have this Gaussian cylinder that's enclosing the entire inner shell like this, and I put some charge Q on it, that just means that Q in is just going to be the total Q. And so this is going to be Q divided by epsilon naught. And so this says that this is E vector is going to be equal to Q divided by 2 pi R L epsilon naught in the R hat direction, so it's radially outward. Okay. And that actually happens to be what the electric field is in the region where between B plus T and C. And we can see that if we draw this Gaussian surface now. So if I put some charge Q on this inner shell, that's going to make this part minus Q on the inside of the middle shell, and then a plus Q out here. And so we see that Q in the region for R is between B plus T and C is also this same thing that I have here. Okay, so the next thing that we want to do is calculate explicitly what the difference in electric potential is between A plus T and C. And so that's to say that delta V is going to be equal to V at C minus V at A plus T. And I did this with capital letters, so let's call this. And let me do it with lowercase because we're already using capital C for the capacitance. So V at C minus V at A plus T is going to be equal to the integral from A plus T to C of E dot dl, okay? So because this is the difference in electric potential I want to find, because the electric field is going to be different in these three regions here, it's going to be the function that I have written here in this region and this region, and it's going to be 0 here. I need to break this integral up into three pieces. And that's to say that this is going to be equal to the negative integral from a plus t to c of this function here. I'll just write this as E1 for right now. So this is E1 dot dl minus the integral, sorry, this is a plus t to b, b to b plus t of E2 dot dl minus the integral from b plus t to c of E3 dot dl. Okay, so looking at these three integrals, one of them is going to be 0, which is going to be this one, because the electric field in that second region is 0. Okay, so this is 0. And now I can plug in the electric field that I have into these two integrals and then evaluate it. And so when I do that, this is going to say that this is going to be minus integral from a plus t to b of q divided by 2 pi r l epsilon naught dr minus the integral from b plus t to c of q divided by 2 pi r l epsilon naught dr. Okay, so when I do these this integral here, what I end up seeing is I'll have a negative sign that's going to be on the outside. This is going to give me q divided by 2 pi l epsilon naught times the natural log of b minus the natural log of a plus t. And actually, it's, this prefactor is the same for both of these. So then I also have here, this is going to be the natural log plus natural log of c minus the natural log of b plus t. So we can use some rules for natural logs here to simplify this. And so what this says is this is going to be q divided by 2 pi l epsilon naught times the natural log of b times c divided by a plus t times b plus t. Okay. So all I did here was I used some rules of natural logs, and that's to say if I have natural log of a plus natural log of b, this is going to be ln ab, and ln of a minus ln of b is going to be ln of a divided by b. Okay? Everybody okay with that? Question? Yeah.
I hate to ask you to repeat yourself, but why are we canceling out that integral from b to b plus t?
This one, because the electric field, this is the portion that's inside a conductor. Oh. Yeah, so the electric field is 0. Other questions? Okay. So now what we have here is, and we should check this to make sure whether or not I need this negative sign or not. So B is larger than A plus T, and C is larger than B plus T, and so that means the numerator is larger than the denominator, and so when I plot the natural log, it's going to look like this, where this is 1. Okay, so it goes from negative to positive when you have values that are greater than 1. And so in order for this natural log to be positive, then the numerator needs to be larger than the denominator. So when I find the absolute value of delta V, it's just going to be equal to this with a plus sign. Okay, so we're almost there to the last part, and that's just to calculate what the capacitance is. And so to do that, what we say is C is just going to be equal to Q divided by the magnitude of Q divided by V. And so that just inverts this. So this is going to say that this is 2 pi L epsilon naught divided by the natural log ln of B times C divided by A plus T times B plus T. Okay, so this is the total capacitance of the system. So that's kind of the first way that we wanted to do this. So we found the difference in electric potential across the entire thing. But really what we can do, if we want to think about it in terms of the equation that we have written here, this is really the same thing as saying I have this first system where this is A and then this is B, and then I have a second system where this is B, and then this is larger, so I'm running out of room a little bit, and then this is C. And what I can do is I can independently calculate what the capacitance of this system is and this system, and if I add them together according to this equation, I get the same answer as I do down here. And the reason for that ultimately comes down to the fact that I can write the difference in electric potential from this surface to this surface as a sum of the difference in electric potential between here and here and here and here, and so call this delta V1 plus delta V2. And then applying the definition of the capacitance, we can plug in the charge divided by the capacitance for each one of these, and so this says that this is going to be Q divided by C total is going to be equal to Q divided by C1 plus Q divided by C2, and then these will cancel, and that's where this equation is going to come from. Yeah.
So if our inner radius of A was like an insulator surrounded by 2 conducting shells, that would change where the bounds were, but the whole setup would still be the same?
So if there was an insulator here, it would kind of be a different question. You wouldn't try to find the capacitance. Okay. So when you're talking about finding capacitance, it's always just with conductors. But I could foreseeably ask you a question where I say, okay, well, instead of having these conducting rings, if I had some insulating rings, and we would just then want to find what the electric field was everywhere. And that would kind of follow the same process that we did earlier in the week, where we said, okay, if we have an insulator, we can say that Qn is equal to the integral of rho dV, and then follow that process.
Okay, so when we see the word insulator, like in a problem, we see the word insulator, we need to think more of electric field versus capacitance?
Right, right. So the only time that I'd ask you to calculate capacitance is when you have conductors. Okay. Other questions? Yeah.
Do you mind just speeding up that?
Sure, sure. Other questions? Okay, so everything that we did here was for adding capacitors in series, and the reason why I can say this is in series is because if I was to go from this inner surface to this outer surface, there's only really one way to do it, and that's just to just walk across here, and it's the same if I walk across there or I walk across there. So this is in terms of a circuit diagram. What this will look like is something like this, right? I didn't have a choice of how I got from the inner surface to the outer surface. But if I do have a choice, and there's a split in the path, like the problems that we're going to do today. So the first problem that I have set up here is you have these two plates. And this region has some permittivity of epsilon naught. This region has some permittivity of epsilon 1. So you have a choice which way to go through this. And what that says then is this is equivalent to a system of capacitors in parallel. And for the circuit diagram, that's going to look like this, right? So I have a choice. I can go through this one or I can go through that one. And what we're trying to get at with the homework or the classwork for today is to think about how we can add capacitors in parallel. Ultimately, what that says is for this system, the equivalent capacitance is going to be equal to C1 plus C2. Okay, and we'll work on those, and you'll see exactly why this is the case. Okay. Any other questions? Okay, so go ahead and get to work on the work for today, and I'll come around and answer your questions that you have.